Hello, and thank you for joining us. I'm just going to give it one more minute to get anybody else that might be last minute joining with us, and then we'll get started. Welcome. This is Alice DiSanto, Associate Vice President of Marketing for Rajant Corporation. Happy to have each of you with us today for Rajant's Man and Machine UGV Integration for Security and Public Safety webinar. With me today are James Laney of Ghost Robotics and Dr. Joe Cronin of Australia Droid Robot. Both are strategic partners of Rajant, as well as unmanned ground vehicle manufacturers. Also with me are Angela Quinn, our VP of Crypto, Robotics, and Drones for Rajant, and Don Gilbreath, Rajant's VP of Systems. We anticipate a lot of questions and further discussions following our time together, so we've included contact information for all of us on this webinar. So please take note and know we will share this information again at the conclusion of the presentation. Know we will take as many questions and comments as possible at the conclusion of the call. And as you listen, feel free to type in those questions and comments into the GoToWebinar dialog box. Thank you. Rajant Corporation will be celebrating 20 years in business next year. That milestone anniversary aligns with the 20-year remembrance of 9/11 because our networking was designed to overcome the networking communication breakdowns and failures experienced by the first responders and emergency service providers on the front lines of that disaster. Our leadership developed a novel industrial wireless network, quickly adopted by the military, that's now used in a wide variety of commercial applications in an array of industries in 57 countries and growing. You'll find Rajant networks enabling autonomous operations in such industries as mining, ports, and public safety. The Rajant solution literally fills the gap of IIoT networking with our kinetic mesh, extending Wi-Fi speed and capacity outdoors and bringing continuous mobile connectivity to enhance LTE. With Rajant, you have pervasive mission-critical coverage and added machine-to-machine communications to work around dense obstructions with low latency and high performance. Though others may claim M2M enablement, Rajant is really the only network that provides continuous mobile connectivity for M2M communications because our breadcrumb nodes, also known as radios, can be deployed directly on mobile assets. As autonomous systems and robotics become operational necessities, their ability to move and communicate is network dependent. Rajant Industrial Wireless Networks literally empowers man and machine working together. Our kinetic mesh breathes life into robots, enabling autonomous operation. And very specific to the security and public safety space, the robotic platforms augment man's capacity to deal with what we call the dirty, dull, and dangerous tasks associated with those industries, making the term security force multiplier more commonly known over the last decade. Our experts have a few goals in mind today for you. So the first one is to empower you with a deeper understanding that when it comes to supporting autonomous and robotic platforms, whether it's up in the air, on the land, in the sea, connectivity matters. The second thing is we want to share how our technology has evolved ahead of commercial networking demands and how we continue to future-proof your anticipated autonomous applications through advanced research and aggressive beta testing. Third, we want to give you a glimpse into two different types of UGVs that solve security and public safety manpower challenges. And last but not least, we want to provide tips on overcoming robotic man and machine integration issues and drive adoption. There's a quote from Steve Jobs: "Technology is nothing. What's important is that you have faith in people, that they're basically good and smart, and if you give them tools, they'll do wonderful things with them." Rajant has been in the autonomous ground vehicle space since our early work in military and mining. That's 20 years of networking for autonomy. Our radios are purpose-built and take into consideration the people factor first. We ask questions like, how can we help a person's productivity? How can we improve safety, profitability, efficiency, operational continuity? It begins with and depends on the network we design, unique hardware and software that enables the man and machine tools you have on hand. Nothing really demonstrates this better than this animation, so if you'll indulge me, I'm going to play this video for you now.
No matter the industry sector, every organization today requires a network that delivers real-time information reliably, anytime, anywhere. Rajant's Kinetic Mesh is the only private wireless solution that can offer the level of mission-critical performance that modern mobile operations demand. That's because Rajant's multifunction breadcrumb nodes don't hand off like traditional wireless networks. Instead, our make, never break method of forming connections allows our proprietary protocol to switch instantly from one connection to another based on connection performance. Here's how it works. In a kinetic mesh network, all nodes are equal and can make multiple connections simultaneously. A mobile or fixed node can direct traffic to any other nodes via multiple paths to ensure that you get vital information fast. Our patented Instamesh networking protocol orchestrates this traffic by always using the best path for each packet between network endpoints. With Instamesh, each node can maintain multiple peer connections simultaneously, making new connections whenever a peer comes into range, and retaining each as long as it is potentially useful to the mesh. If one path becomes degraded or blocked, the network will automatically redirect traffic to the best connection. As a result, connectivity remains continuous for reliable, real-time data delivery at low latency, even as the network grows. Kinetic mesh networks consistently outperform the competition in mission-critical scenarios due to their ability to make intelligent, autonomous routing decisions that result in a higher level of reliability, especially where mobility is required. Take, for example, police responding to an automobile accident. With a properly designed Rajant network, dispatchers have visibility to the accident in real time. Police and EMTs have real-time mobile access to voice, video, and data to help coordinate first responder efforts while in transit, and can stream live video from the scene to required medical personnel. By comparison, when mobility demands are high, traditional Wi-Fi and mesh networks often fall short. These networks typically employ break before make or make before break approaches to connectivity. In traditional break architectures, mobile nodes can only talk to infrastructure nodes, not each other, via a single connection. When a mobile node leaves the range of its current fixed access point, it loses connectivity and must then find and reestablish a connection with the next access point along its path. Even if the network is able to scan for and determine its next path prior to handoff, it cannot use this newly made connection until the old one is broken. It still can only make one connection at a time. Breaking connectivity over and over leads to dropped data packets, high latency, and compromised application performance. Degradation becomes worse when trying to scale to hundreds of roaming assets. At Rajant, we believe that a network should adapt to support all voice, video, and data assets that reside on or traverse it, no matter how those assets change or move. We call this a living network. Don't settle for anything less than the mission-critical reliability of a living network, enabled by Rajant's make, never break approach. It's connectivity evolved.
To empower you with a deeper understanding that when it comes to supporting autonomous and robotic platforms, whether air, land, or sea, connectivity matters, let's meet Angela Quinn. A recent powerhouse addition to the Rajant team, Angela is a sales leader in the IoT and IIoT networking industry as an individual and as a manager of global and national sales teams. Angela, the floor is yours.
Thank you, Alice. In our next slide here, I'd like to point out the differences between our point-to-point technology, point-to-multipoint technology, and the advantages of our world-renowned kinetic mesh breadcrumb technology. In a point-to-point demonstration here, you can see it is literally one linear link from point A to point B. In the point-to-multipoint demonstration here, you can see it's a single point spreading out to a hub and spoke environment to multi-points with multiple end user devices available for connectivity and being a single point of failure. In the mesh environment here with our kinetic breadcrumb technology, you have this significant advantage of multiple radios, multiple links, and multiple frequencies. In the next slide, we can demonstrate showing you this as we overlay in a city or municipality environment. As you can see, there's robots, drones, man-to-vehicle, vehicle-to-vehicle communications, and man-to-machine communications, all in an autonomous environment. Rajant's kinetic mesh environment and solutions provides you and your municipalities and public safety venues the availability of seeing video surveillance and real-time data in sub-millisecond latency advantages over any other technology and mesh in the world. In the next slide, we'll also be demonstrating, as you can see here, bots communicating directly, ground bots, as well as to buildings, cameras, manned vehicles, manned devices, IoT devices, and drones. This is a significant advantage as we are evolving and have evolved in small devices for the bots, drones, and IoT devices in environments, harsh environments where weather, dust, and environmentals are critical to success in mesh environments security-wise. And in the next slide, I'd like to demonstrate here the traditional mesh networks. On the left here, you can see the hub and scope perspective with our nodes. The yellow dots represent a single node spoking out to the end devices or IoT devices. Each one of the hubs is backhauled by a 5.8 frequency. As you can see on the right, in a kinetic mesh environment, we have multiple frequencies connecting to all of the devices, whether it's an end device with our breadcrumbs as well as the nodes. I might point out that you can see the differences between the red being the 5.8 frequency, the 2.4 frequency represented as the green. So in certain environments, it's going to take the path of least resistance based on the frequency and availability of the transmission. In addition, we have frequencies in 4.9, 900, and the 2-point frequencies. And in our next slide, you can see the advantages that we have. If on the left, a traditional mesh environment were to lose a single node, it loses all the adjacencies to the other nodes, as well as completely taking out the end mobile devices via the Wi-Fi in that particular environment or region. If you look to the right on the Rajant kinetic mesh environment, you see that not only have we lost a single node, but we've not lost any of the adjacency nodes or any of the end devices. So this is critical in a ground bot environment to communicate to the IoT devices, the mobility applications that we can provide. Our next slide will demonstrate some of our military spec that we have world-renowned technology and security above and beyond any other mesh products on the planet. With this being said, you can see the full encryption with triple DES as well as mil specs for military grade product. In addition, we are a layer 2 radio providing multicast better than anyone else in the industry, thus giving you the most secure network infrastructure with no need or concern for enumeration as we do operate at a layer 2. With that, I'll pass it on to our next provider here.
Yeah, thank you. Thank you so much, Angela. That was awesome.
You bet.
Next up, Don Gilbreath. Don focuses his 30 years of product development, engineering, project management, and specialized technical sales on extreme industrial IoT opportunities for Rajant's industrial wireless communications technology. Don travels the world and literally traverses land, sea, and air to stretch the capabilities of networking for all types of autonomous platforms. Welcome, Don.
Hey, thanks, Alice. Rajant has a whole family of products, as you can see from this slide, from our hardened military-grade radios down to our smallest edge devices. And many applications, we use all of them. What we've been using recently a lot was a new model, our DX2, which is our lightest model, and it finds its way into not just aerial platforms, but some small demanding kind of ground robots. Give me the next slide, please, Alice. So here's like a snapshot. Besides working with all these great strategic partners like Ghost and ADR from Australia, I also get to work with a few teams that are doing DARPA programs. This is a particular picture from right before the COVID lockdown in February, where we were running a DARPA program that's called Offset. And Offset's mission is a man-machine teaming operation with upwards to 250 air and ground robots, all interconnected and potentially operated by one operator, one swarm commander. What you'll see, if you can see this picture here, is on the right, there's a group of drones. Those are all outfitted with our DX2s, and primarily it's because of the weight profile, right? And on the left, there's these ground robots that are more, used throughout academia. They're used in a lot of sort of research areas, and they're outfitted with our ES1s, which have dual frequency capability. Wherever we can use multiple frequencies, we like to do that. And this is a classic case where the ground robots could handle a little bit larger radios. So we sort of fit the radios, form factors and power consumption based on what we're trying to outfit. Next slide. So here's a great snapshot of a single team, a single fleet. And there's about 70 or so devices here. And like I said, this was February timeframe. Now we're starting to get out of this sort of COVID lockdown area, and we should be turning on upwards to about 100 in the next month. And the goal, again, as I said, is 250. What you'll see is like these ground robots, they have not as much sophistication as some of the guys you're going to listen to next, but they do have simple LiDAR. They've got enough co-processing power to sort of avoid falling off of cliffs and running into each other. But their main job is to actually be able to start doing sort of gameplay. A classic example is these ground bots might be sent off to just explore an area, and DARPA made it a little easier for the play in that they provided these sort of QR codes that are called April tags that are representing things like fuel or bombs or good things, bad things, and basically these robots, when they come into scene, they find them. They basically are other robots are essentially bidding in real time to assist that particular find. A guy that might be a tanker says, "Hey, I need more fuel, or I could use fuel." And this level of gameplay is actually going on without any human operation. There is a swarm commander, but it's part of the gameplay. Go explore, and robots that can help, please help. And it's amazing to see this level of sort of edge processing running, which is fully distributed, matched with Rajant's Instamesh, which is fully distributed. And it's a classic case where scaling can go very large, and that's what we're shooting for. Next slide, please. So obviously we're interested in the network health in these kind of operations. Here's a shot of one of our guys in a control van during this exercise in February, where we're kind of looking at all the spectrum of the radios. We're looking at all the data. We're looking at the CPU of each one of our radios. Not that we needed to, we just wanted to see how well it performed and how well it will perform as we scale up. I think there's one more slide, right? So here's a starting gate. There's a few robots here. This is about 8 city blocks. This is in a mock city that the government provided, where the robots were essentially tasked to do some jobs. You might see some of those little QR codes or April tags, as I was describing. Some only drones can see from the air, and others that the robots can see from the ground. And again, they are acting in a way to assist humans, but act in a very autonomous fashion. And this obviously plays well to public safety and fire, where you have this force multiplier of an operator who may have multiple robots, whether air or ground or sea, that can actually assist in an operation, whether it's figuring out a fire line from a big fire, or breaching a building, or various applications that pub safety might be using. What to me is exciting is to see all of this truly distributed work come together, where there's not really a control room anymore. There's various stakeholders, but it's not the classic network that you would see, and it's not the classic robot case that you would see. And that's why I'm very excited to be involved with this. And I'd love to pass it on.
Yeah, those are super cool toys, Don. Thank you so much.
Thank you.
Hey, all right. Welcome our first UGV manufacturer, Australian Droid Robot from Australia. Founded in 2014, Australia Droid and Robot specializes in remotely operated ground and aerial vehicles that travel into those dirty and dangerous crevices or airspaces to autonomously inspect what can often be inaccessible or uninhabitable areas for safety reasons. Dr. Joe Cronin, thank you for being with us, and please take it away from here.
Great, thank you so much. Australian Droid and Robot started some years ago when, having spent time in the defence industry, we saw the incredible work that the US Army had done in terms of robotics to keep people safe, and particularly the explosive ordnance disposal teams, who had developed systems to telepresent themselves, to deal with a hazard from a distance. And when we worked in the mining industry, we saw so many things happening underground, where people were being sent in to evaluate a situation. And we immediately recognised that the great contribution robotics could make to safety by having people and the hazardous tasks separated. Our motto is safety by separation. You know, we try and keep people safe and send the robots into danger. So we produce a range of robots. We have some off-the-shelf robots, but our real strength is when customers have a problem with our manufacturing, design and engineering capabilities and experience, we can develop a custom solution, as we like to say, faster than some companies can appoint a project manager. We can have it delivered. So our robots for remote inspection and projecting in the environments. And we spent many years playing with networks and suffered handover problems with the robots when they went from one access point to another, and then we ran into Rajant, and we haven't looked back. It is the most amazing networking capability we've experienced, and we don't know what happens inside the little boxes of Rajant magic, but it just works. It works every time. All right, can we move to the next slide, please? Excellent. So I said our mission is to provide safety by separation. So we provide, particularly for the underground mining environment, a range of high mobility robots that can be sent into areas where the ground is unstable, there could be gas there, old workings where there hasn't been ground support for some time. And typically it's gas sampling, it's laser scanning, and it's video survey. Again, we see separation, you know, particularly the combination of new sensors, robotics, artificial intelligence allows you to separate personnel from hazards, and we see separation as a new control, a new safety control that should slide into the traditional hierarchy of controls as the first choice. As in security applications, in military applications, and underground mining, there's similarity. You can't eliminate the hazard. It is part of doing your job. You can't substitute the hazard, but separation becomes a more powerful control than an engineering control. When an engineering control fails, the personnel and the hazard are still in the same place. They're co-located. But with separation, when that fails, your personnel are still safe. Next slide, please. Okay, so one of the reasons that robotics hasn't sort of expanded as quickly as it could have is that people really don't understand it. It's too complex, it's a bit sci-fi for them. But in this example, you can see where you have a small robot, which is like a remote control toy, and it's doing an under-vehicle inspection. Now that vehicle is simply sitting there. In an application where a person would have to get under that vehicle, it would have to be locked out, the engine would have to be off, wheel chocks would have to be engaged, and you can't see what it looks like when the engine's running. So this is simply a robot which is becoming just another part of a toolbox. You know, for a mechanic, they've got spanners there, they've got their engine analyzers, and now they have robots that they can drive under vehicles to see where exhausts are leaking and diagnose a number of problems. It is simply a tool that goes into the toolbox. And as we say, you know, start small, and that robot is line of sight controlled. But when you have multiple robots or you need to project beyond line of sight, that's when we bring in dynamic mesh networks, and we can deploy a number of robots, and they can relay from each other to do more complex inspections. But you know, for any application, particularly security applications, start small. Just have one robot and then build on that system. And the beauty of our products and the beauty of the Rajant products is as you build, they just plug together and you can expand. Next slide, please. So this is we've done a lot of mining work, and these are two examples of a mine control room. And what we've seen in mining over recent years is the expansion of central control rooms, where the person responsible for the operation and the operators themselves now have, instead of being underground in a single vehicle, where they've only got the immediate vicinity that they're aware of, they're now in a central room brought together with much greater situational awareness of what is happening around them. And decisions can be made on real-time data and a lot higher granularity of data. In the picture on the right, the screen at the back, you can see the entire mine operation and where everyone is in the mine. Similarly, in security applications, when you have a high-value asset, your control room shows you where all of your people are and what's happening around you. The beauty of a control room connected via network is that, you know, in a situation, you can launch drones, you can send out ground robots, you can, you know, launch fixed-wing drones as surveillance platforms, and we'll cover that later. But instantly, in any event, instead of sending people out to find out what's got wrong or what's happening, you have a much expanded situational awareness where you can be looking down from above on your entire operation. And again, with a dynamic mesh, it doesn't matter which vehicle you send up, they will instantly mesh and you will have those video feeds available. Next slide, please. So this for us is the one of the real benefits of the dynamic mesh network, where it's make, not break. The trace below, you can see each color represents the feed from an access point as a robot is traversing. You can see that the green to the blue is a relatively smooth handover. However, there was confusion at the end of the blue trace when the robot let go of the access point, then grabbed it again. And every time that happens, the robot stops. In some networks, that has to reconverge. If you're driving an autonomous vehicle at any speed, it will stop, or you'll lose control, you'll lose the video feed until it's re-established. The beauty of the Rajant network is that it never breaks. And with the breadcrumb tools, as you've got robots moving around, you can monitor the signal, and you can, you know, easily know when you are getting to the limit of that signal, and you can send another robot in. It will instantly mesh and then double the range of your reach. We have latency now sub 100 milliseconds with high definition video feeds. All right, next slide, please. So this is a typical example of what we can do. We can have a ground station, we can have robots in the field, we can have drones in the air, and they will instantly become part of that network. And the other great thing about the Rajant networks is when you introduce a new node or a new radio in a vehicle, the whole mesh doesn't have to reconverge. That when it's meshed, that radio will just pop up and you'll have access to the video feed or the sensor feed from that device. That's really important, because if you start taking out members and reintroducing members of a network, it can play havoc with traditional Wi-Fi networks. And again, by having multiple robots and the ability to relay signals from one to the other, you can extend your reach very quickly. And if you have an existing network around an asset, then a fixed network with your regular camera feeds and sensor feeds, then the robots that you send out will simply expand that network. It'll feed straight back in. Okay, next slide, please. So a typical example for us is we'd have an operator with a base station controlling any of the robots, and then we'd get the video feed, and then any of the other vehicles we have would mesh. And a typical example is you could have a ground robot looking for something in a field, and then you could launch a fixed wing drone with a DX2 in it. That fixed wing drone not only provides aerial video feed, it also acts as a relay point for the ground robots. So even though those ground robots might have walls around them and in thick vegetation, because they're really relaying off the aerial vehicle, you have a very rugged, very reliable network. And then you can throw a rotary drone in or another ground vehicle, and the more you throw out there, the better your network becomes and the more reliable it becomes. In traditional Wi-Fi networks, the more you throw out there, the more confused it gets and the more delayed your communications becomes. Okay, next one, please. So this would be a typical example. You know, perhaps after a seismic event in an underground mine, we'd send a robot in to do a laser scans, do a video survey, and where the mesh may or the network, the existing network may have been compromised by that seismic event or by a blast or a gas explosion. As the robots go in, they create their own network to give you the reach to get to where you need to go. And one of the great things about this system is often after a serious event, the authorities are involved and people spend a lot of time working out how they recover from that event. You know, under what they do a risk assessment, what conditions can we send people in? But with robots, you don't need to do any of that. You just send the robots in because there's no safety issue. And by the time the authorities arrive, you already have data. You've already started your recovery, and then you can make decisions based on that data. Thank you. Next slide. So this is a typical example of one of our robots. There is a mine that wants to go into old workings. They have a lot of bats in the old workings. They can't send machinery in because the bats are protected and the machinery can hurt the bats. So we have a robot that can go a long way into that mine with lots of flashing lights and loudspeakers that can, you know, one, look and see where the bats are, and two, hopefully encourage them to move out. And this robot is just an extension of a person. Again, it's just a tool. It means that when you get to site, it's another tool you pick up from it and allows you to do work remotely and safely. You know, it's man and machine working together. It just extends your reach and provides also that separation and safety. Okay, next one, please. So again, a typical example in a mine. In this case, we're exploring an abandoned mine to see what the situation is. There's a bulkhead in the mine that was holding groundwater back. So what we would do is we would send one ground robot 100 meters into the mine to the first intersection, and then send another one to the next intersection, relaying the signal and extending our reach. And once we've established that network, and I guess it's the case same as the case in Don's 75 robot mesh, that once you establish that network, you can then send high value assets in, knowing that you have a robust and stable network to do, we call it the end effector. So we put essentially almost disposable robots in to see what's going on. Once everything's established and we've seen what the conditions are, we'll send the end effector in to do the job. But again, the person sitting outside the mine in the beautiful Queensland sunshine, control everything remotely. And it doesn't matter what happens in that mine, that person is not going to be exposed to hazards. It's just an extension of your capability. Okay, next slide. So this is, I think there's a video, yes. This is one of our favorite toys. It's called the Seeker. This is a very lightweight plane with a remote camera that just drops down, a network camera, and provides a video feed, and it's got a good zoom camera and it's very well stabilized. But this is the typical thing, if you're in a situation and you're in a security control room and you're guarding an asset and you see something happen, or a sensor goes off, or you think something's happening outside, what's the first thing we do? We send a person out. We send that person into danger. Instead of sending the person out, just throw this thing in the air and go and have a good look from above. The camera on this is just like your typical security camera that's bolted to a pole on the ground, except that it's 500 feet up in the air and it's providing exactly the same video feed. And you can add multiple drones, multiple robots you can send out to see what tripped the alarm, or just to do a continuous patrol of the premises. Forget the fact that it's a robot, forget the fact that it's a drone. It is simply a mobile camera. It's like picking up one of your security cameras and just throwing it somewhere in the sky. Because all of these vehicles are autonomous, you can hit a button, they will launch and they will stay in one position for as long as you have battery. And it is like having a 500-foot steel pole with a camera on top that you can move around. It just extends, we pay hundreds of thousands of dollars for our security in our network, and this expands it very cheaply and efficiently. Okay, next one, please.
Thank you, Joe. Thank you so much.
That's great. Thank you very much.
Yes, you're off the hook.
Excellent.
Welcome our second UGV manufacturer, Ghost Robotics, who share the same corporate headquarter area with Rajant in the Philadelphia metro. Founded in 2015, Ghost Robotics specializes in legged robotics and in the market for highly agile and fast teleoperated and autonomous unmanned ground vehicles for military, homeland security, public safety, and enterprise inspection and security applications. Their UGVs, unlike ADRs, are defined as quadrupedal UGVs or QUGVs for their four-legged ability to traverse an array of terrains similar to a dog. James Laney, thank you for joining us, and please tell us more about Ghost Robotics.
Thanks. Yeah, so at Ghost, we believe that the static robots of today will give way to dynamic legged, wheeled and tracked platforms, and eventually have these mechatronics and organic hybrids with thousands of actuators to really capture the behavior fidelity of life. So we believe it's not a question of if, but a question of when. And that's what we're focused on building at Ghost, is the core control and the foundation of those systems to be able to capture a robotic system that's able to exist in the wild and really surpass our current state of the art. So why legs? Well, as you saw in some of the examples, the wheeled platforms are only so big. When you have legs, you're able to navigate all sorts of different types of terrain, especially when you get into the situations where you don't want to send a person in, where you actually don't know what the environment is. You just have so much more flexibility, having the ability to control all your many degrees of freedoms. We also, with our unique electronics and control design, allows us to have much higher endurance than some of our counterpart vehicles and drones, and reach up to 7.8 miles with our current robot, but soon with a larger battery, we'll be able to hit something closer to 10 miles. But many ground-based platforms are very small and short. However, with the legs, you have just a much higher vantage points, which really gives us a better operability presence just right off the bat without having to put a boom or a mast that can really, get stuck or make it difficult to navigate the robot. And then finally, something that we weren't really aware of until we started getting into it was just the user acceptance. And again, we're hearing from our enterprise customers and customers from all the groups that we're working with, that if given a choice between wheels or tracks or legs, they all pick legs. And the question that we all ask ourselves is, why is that? Clearly a wheel platform would be better if you've got flat ground, but we think that's, the hundreds of years of evolution of, man and dog, which is really just, it's really important to capture in order to have a really strong man-machine teaming system. Next slide, please. So this is a glimpse of some of the projects we're working with. Right now, a lot of our big projects focus primarily with the DoD across various agencies. And just now with our latest robot, we'll be getting more into more of our enterprise customers and looking more into inspection and security. Next slide, please. So this is our latest robot. This is our Vision 60 V4 that will begin shipping actually next week. And over the course of the month, we'll ship about 20 of these before we build another batch. And that's something that we think is pretty different for how we look at building robots, is that we build and break and fix our robot at very high scales. So about every quarter, we release a new robot. We get it out in the field. We get feedback from our customers, and then try and integrate that as best as we can with the next revision, with our final enterprise model being done later in the fall, and then our military version finished early next year. Next slide, please. So looking into some of the projects and the use cases, one of our biggest ones is ISR, ISTAR, Intelligence, Surveillance, Target Acquisition, and Reconnaissance, which is really just a fancy word for remote inspection. Currently, we're working with a number of DoD agencies across the board, all seeking to use our bots to extend the reach for a variety of missions and really take humans out of the equation and out of harm's way. In the upper right, you can see our robot participating in an Air Force exercise providing strike targeting data for a battlefield, a battleship off the coast several miles away. And in the lower right, you can see our bots kind of scouting ahead, really ensuring that the area is safe before the troops continue. Next slide, please. Some of our newest interest, though, has come from the Suburni area for chem, bio, radioactive, and detection use cases. What used to be very expensive and very heavy sensors are now being shrunk down and becoming lower cost. So many organizations are looking to use our bots to mount a variety of sensors to make really the ultimate Suburni detection robot to sniff out hazardous materials, volatile compounds, or even drugs in some cases. Next slide, please. But the same robot that we're kind of designing for the military that can just live and exist in these harsh conditions and operate in any environment is the same robot that's needed for something closer at home for public safety and emergency management. So all we need to do there is just swap different types of payloads, and we've got a different robot able to adapt to a different use case and leverage various machine learning algorithms or computer vision algorithms to really enhance that capability. Next slide, please. And of course, one thing with our longer ranged endurance, we see that our robot is able to really extend and augment the fixed sensor systems that are used to secure various bases or perimeter patrols, and enhance that capability to provide 24/7 autonomous security in these types of applications. Next slide, please. And finally, something a little bit closer to home, and this is something, you know, we really weren't too sure about, but it makes so much more sense. We take for granted that, you know, we can pick up our cell phone and call each other, but this often isn't the case in contested environments or in an environment that, an event happened, whether it's weather related or something else. But using our robots as these comms mesh repeater nodes, putting the Rajant systems on. In the lower right-hand corner, we've got an LTE network. We can enhance that network system. We can allow that mobility network to move with you and extend your reach and be able to just maintain a much better comms throughout the environment. Next slide, please. This is a video montage of our older robot, our version 3.9, that's getting replaced by the version 4 coming out soon. This is the Prime Minister of Singapore actually trying to shake the robot and just kind of proving the stability of our system. So everything that you're seeing here now is the robot is actually operating in what we call blind mode. And so what does that mean? It means that right now, when it's, as you see in the video, it's actually operating without any preconceived notion of the environment around it. It doesn't know that there's the rocks, the curbs. All it's able to do is just react, and it can do all of this very efficiently and very quickly with our control system that allows it to just maintain its stability and really act as the reptilian brain. So here you can see one of my colleagues, Gavin, the co-founder, actually perturbing the robot with a really heavy medicine ball, and you can really get a glimpse of just how fast the robot's able to react and maintain stable, which is really important when you're getting into these environments where you don't know what it's going to look like. So your sensors can fail all the time. This happens in various environments, but that core stability platform is there under the hood to make sure that the robot stays stable. Again, this is just another example of the robot able to traverse up the stairs without having to rely on its vision sensors to know that the stairs are there. Here you're seeing the robot actually just given a simple command to go forward. You don't really, the video didn't do justice, but it's extremely steep. And so the robot's sitting there carefully trying to place its next foot, all just doing so from its internal sensors to be able to just feel the ground underneath its feet. One thing that's pretty interesting about our robot as well is it can operate completely inverted, which is important in some of the applications where you get in and don't know what's happening, but it is also able to self-right itself. So, you know, this capability again is all baked into the core platform. So depending on what's going on, the robot can make these decisions to self-right itself or to operate completely inverted, because at the end of the day, you know, the robot just needs to get there. It needs to do the task. It needs to provide the data back, the comms, and get the information to the user to be able to allow them to make important decisions. And again, just trying to show the stability, the robot's also able to think and say, hey, I'm getting a little bit too disturbed, and actually drop down into what we call the cat pounce to get back up and re-engage this stability. So with all of that put together, that makes for a core, a foundational platform that when brought out into the field is reliable, is stable, and can go just about anywhere. This is some later clips of our version 4. This is the one that we're about to ship, going around our facility, giving it a little test run. All right, next slide, please. So how do these robots work? So at the top, it's a modular system. So the legs, the sensor head, the compute box, the battery box, all of these components can be removed and be field repairable in under 2 minutes. All of them are enclosed themselves, IP68 for our newer versions, which really is important for these types of environments. One of the things that allows us to, be so reactive though, is we removed all the hardware complexities that you find in traditional legged robots. So there's no springs, force sensors, or other types of complex mechanical actuators, and do all of this in software instead. And this allows our platform to be so dynamic, but also allows us to scale it to various sizes. So the table below, you see the Vision 60. That's the model that you've seen in the video. It's our kind of flagship robot, but we're also able to build robots a bit larger and a bit smaller up to a certain size scale. We have another robot that we call the Spirit, which is primarily for R&D, but it's not being displayed here. But that's a much smaller robot, but it uses the exact same control algorithms, the exact same software, and the exact same electronics, just scaled down. Next slide, please. So looking a little bit deeper, one thing that's pretty unusual for these types of platform is we provide, all sorts of ways for the customers to engage with the system itself. So we have a low-level API, which allows customers to go in and actually reprogram the gates at the joint level and teach it all sorts of new behaviors. So some of our research customers actually can train the robot to do backflips and cartwheels, climb fences we've seen in some of our other robots, which is, really opens up the capabilities and allows customers to come in and design what they need for their application. Then on top, we've got a NVIDIA Xavier that's able to process all the sensor feeds that you see on the right, which is really important when we're trying to establish a system that's able to negotiate and navigate all of the unknowns that you want to send the robot into. And all of that's accessible, again, from a high-level API to be able to interface with various ground control stations, different remote controls, different autonomy level layers, and all provide kind of the all-be-all robot platform for your remote sensing applications. Next slide. So this is a picture from the DARPA Subterraneous Challenge. Here you see on the right, 4 of our robots outfitted with the Rajant DX1 breadcrumbs, which have the dual frequencies. Those large circular things are actually high gain antennas. And on the left, you see the base station, another Rajant product, the ES1. And one thing that the Penn team did very well was manage comms. And so the entire time, the robots were always communicating with each other inside the mine. And it was done so well that some of the teams afterwards came and asked us about the types of radios we were using. And one of them has now switched to use the Rajant system. So this is, again, trying to show that it's so important to have connectivity in all these unknown environments. And Rajant's really been able to prove that to us here with the Subterraneous Challenge.
Thank you, James. That was awesome. Terrific overview of man and machine learning about what the right network can do to empower UGV integration for security and public safety. And I most appreciate your diverse perspectives on this topic, from Angela to Don to Joe to James. Rajant's slogan is, if it's moving, it's Rajant. To be a security force multiplier, UGVs require a fully mobile, fully redundant, resilient, and multi-pathed and secured network. Whether on wheels or on legs, as we saw, Rajant's kinetic mesh enables man and machine to effectively tackle those dirty, dull, and dangerous safety and security applications of today. So as promised, we have a few more minutes here, and if it's okay, we're happy to go over the hour to answer them. So let's turn to our panelists to address the questions and comments that we've received so far. Continue to add them in if you want, but I'm going to start with a question from Jonathan, and it's directed at Ghost Robotics. How are you able to reach the endurance numbers?
Great question. So one of the things that we've done differently with our robot, and this is kind of the foundational strategy that Gavin put together, was instead of utilizing multiple Intel i7s, which is typically found in a lot of other legged systems, all of the control platform is actually handled on a microcontroller running with using less than 1 watt. So all of that power that would be to operate the multiple i7s is now gone. So we're able to utilize that to enhance the endurance of our system.
Excellent. Thank you, James. Okay, the next question is for ADR, and it's coming from Chelsea. Do you have a specific Rajant node for your operation? And if so, which one?
Good question. No, we don't. One of the great things about the Rajant toolkit is that for our flying drones, we use the DX2s, which are very light, magnesium, size of a couple of matchboxes. For our big robots, we use ME4s, very rugged, dual bands, and then for the normal applications we can use ES1s. One of the great things I love is going to trade shows where we partner with Rajant, because I don't know whether you know this, Don, but occasionally you guys go home without some radio gear. So whenever there's new product, we tend to latch onto it. You know, depending on the application, whether you need dual frequencies or operate on a single frequency, there's a range. It's application specific, but at the end of the day, you can turn them all on and they will all just join together instantly.
Joe, now you've answered a burning question about shrinkage.
Yeah.
Okay, so the next question, Joe, you're still up, comes from
Right.
Mark. And so Mark asked, traditionally technicians spend a lot of time optimizing the position of antennas, but here the vehicles are mobile. How do you know if the network is healthy?
It's a really good question. One of the things we found when we started this years ago is as robots move over undulating terrain, the angle of the antenna changes and you can win and lose signal quite quickly. One of the things with the Rajant network is the breadcrumb suite. Well, two things happen. One is because the ME4s and the DX1s are 4 aerial radios. We can have aerials at slightly different positions. So as one moves a little bit out of optimal position, the other one moves into that position. Also, the software that controls or monitors the mesh network tells you quite clearly what your signal strength is and when you're beginning to run out of signal. And you know, in the old days when we were using traditional Wi-Fi products, that could change very quickly. What we found with the Rajant gear is the drop in signal as you move away is very predictable. I hope that answered the question.
Yeah, well, I do too. I didn't ask it, but yes, I hope it did. Okay, next one is from Ruben, and it's to you, James, at Ghost Robotics. How does the robot know where to step?
Yeah, great question. So using the blind controller, the robot doesn't quite think about it in that terms of exactly where to place. Instead, a good analogy is if you were to close your eyes and then someone behind you, and hopefully that's someone you trust, were to tell you to walk forward, turn left, turn right, you'd be able to do it no problem, right? You're fully capable of locomoting your joints and you can continue to move through the environment. And as you encounter different things, you might stub your toe a little bit, but then you'll just recirculate the leg. That's what the robot does under the hood by itself. It has that reflexive, that blind reflexes, which is important in case the vision system were to fail or lag behind at any given time. But when we turn the vision system on, which it has access to, that's when we're able to plan ahead and strategically place its feet. So, you know, just like us, you're not always looking down at the ground and thinking about exactly where to place your feet. And so the robot does this kind of dance between the two systems, making this decision and basically can say, oh, the ground looks a little bit tricky. Let me look down at my feet. Let me use my vision sensors to place my feet. But if I'm on a flat ground or something that you know, isn't challenging, you're just going to walk as you would normally. And so the robot is able to do this in real time, flip-flop back and forth, and make those decisions by itself.
Okay, thank you. I think I can squeeze in one last question here, and it will be at you again, James, and it might be sort of related to the last question. So what do you mean by a robot operating blindly? How does it know where to go at that point? And this is coming from Teresa.
Yeah, so very similar, right? So it's a layered system. the decision of where to go, we allow that to come from something else, and that something else could be the autonomy system that's running that has a map of the environment, or maybe it's making the map as it's going along. Maybe it's a remote operator, and they're just making that decision in some cases, or it's a programmed route of waypoints where there's really no decision to be made there. It's just go to the next one, go to the next one. And so the touching base on the previous question, the low level of the robot is able to navigate given these little waypoints, but it is true that without having some higher notion of the environment around, it will bump into something, which is why we turn the vision system on and be able to provide obstacle avoidance and other types of features that you would want in your robot.
Excellent. Okay, so we'll end there. Great thanks to Angela Quinn, Don Gilbreath, Joe Cronin, and James Laney. It's been my pleasure to spend time with each of you and host this webinar. And to the audience, there's much appreciation for your time and attention. Please know that after we finish up here, you're going to get a survey, and we'd really love your feedback. It helps us to continue to refine and build on the webinar series that we've had out over the last, almost 2 months now. And contact information for all 5 of us is on your screen. Please know that the full recording of this session will be live at rajant.com under our section called Webinars for your reference and for sharing with others seeking similar information as you. Be well in the days ahead, and thank you again so much for joining us.
Thank you, team.
Thank you.